All right, so today we are going to discuss combination circuits and how exactly we can solve for each part of the circuit. Now, on a usual test, they will not have you solve for the individual resistance of the individual current, at least not at a high school level, but they could. So let's ensure that we know exactly what to do. Step one, we're going to look at the series to parallel circuit first. Going from left to right, we're going to follow the following steps. Step one, we're going to start analyzing the parallel part of the circuit. The reason why is because we want to deal with the more complicated section of the circuit first. The more complicated part is usually the furthest away from the battery. So you always want to go out and work your way back to the battery. Again, always start away from the battery and work back towards the battery. So by analyzing the parallel part of the circuit, we've started that process. We're going to combine the two resistors in parallel such that they become one. Once you've done that, you've combined those two resistors in parallel, you will now see a series circuit. Cool. That series circuit is going to make things a lot easier because now you can just use series rules. Well, next up, combine those two resistors in series, and now you have a simple circuit, and everything should be super easy from here. Because what you've actually done is simplified your once complicated circuit. You went from a series to parallel circuit to a simple circuit. Well, what does that really mean? That means that if you know the total voltage, you now know the total resistance, you can find the current. Now, once you find the current using Ohm's law, you kind of want to start working backwards. But like I said before, normally they would not have you find each individual piece of a complex circuit or combo circuit. They would have you more or less stop here. So I'm going to take you step by step on what you should be doing to solve for this series to parallel circuit in a collapsing kind of format. So first things first, what you're going to need to do is, well, find your total voltage. Done. You can find your total voltage if you look up at the question to the top right. Joe has built a circuit with R1 being 2 ohms, R2 being 2 ohms, and R3 being 2 ohms. The total voltage equals 30 volts. Easy. Now, what we are looking to do is find the equivalent resistance, the equivalent current, and the equivalent power. Now, when you see the word equivalent, what you need to think of is total. Again, when you see the word equivalent, think of the word total. That will help you get through the problems a little bit easier. Plus, physics is just another language. Just get used to it. So I could say the equivalent voltage of this circuit is 30 volts. Again, I could say the equivalent voltage for the circuit is 30 volts. So next, we need to identify our resistors. Boom, there they go, they're all 2. That was easy. And we get that from the problem. Well, what do we not get from the problem? We do not get the total resistance. And we don't get the total resistance. What we need to do is start breaking this stuff down. The way we want to do that is by looking at what part of our circuit is parallel, what part of our circuit is in series. Well, that's when we need to go back and number some things. Hi. Well, let's start here. Our terrible color. R1, R2, R3. So from just labeling, we should be able to notice that R2 and 3 are in parallel with each other. And R2 and 3 are in parallel with each other. So we're going to start by simplifying those two resistors into one. And we're going to simplify those two resistors into one resistor. Well, how do we do that? For each part of the circuit, you're going to use the corresponding rules. For a parallel circuit, use parallel rules. For a series part, use the series rules. Well, we should all know that in order to find the resistance In a parallel circuit, you need to use the flip, add, flip method. And if you don't remember that method, you need to go look at my previous video to check that out. But to simplify it, you have two resistors, you invert each resistor, you add them together, and then the last flip is going to be that inverse. Again, exponent -1. Again, if you have not seen the flip, add, flip method, I suggest you go back and watch the previous video on parallel circuits so that you can get a little more grasp of it. But we realize, dang, our resistance for resistor 2 and 3 just equals 1. Again, the resistance for 2 and 3 are just 1. Well, now that we have that in place, we can solve for the total resistance, and I promise it's easy. Because resistors 2 and 3 really just equal 1, we can add them together to R1. Let me slow down. We can now add the resistances together in series to get our equivalent resistance. The total resistance should be R1 plus our new R2-3. So it should be R1 plus the combination of R2 and 3. Well, the total resistance becomes 3. And total resistance becomes 3. Key takeaway here is that you have to be able to solve the parallel part in parallel. And then once you've done that, treat everything like it's in series. All right, so next. We have all of the resistance column complete. As much as I would love to deal with the voltage column, the best thing to do is go ahead and find the equivalent current, or the total current. The way we can do that is dividing our total voltage by the total resistance. So 30 divided by 3 gets you 10. All right, so now we have our equivalent current. We can now move on to the next step. We want to look back and see, can we figure out the current for other spots in our circuit? Again, let's see if we can use the other spots in our circuit to figure out the current. Well, we should remember, because resistor 1 is in series, we can use series rules for resistor 1. Again, resistor 1 is in series. Let's use series rules for that resistor. Because in a series circuit, current is constant, boom, you can just put the current in that spot. But that doesn't really fill everything out for us, does it? Because current in a parallel circuit is not constant. We're gonna have to hold off on the rest of that column. It's like we're playing Sudoku. We know a few things, but not everything. But hey, what we can now figure out is, oh wait, we have resistance and current. Can't we find the voltage? And if we can find the voltage for one part of the circuit, we should be able to find the voltage for the other part. Now, we get a voltage of 20 volts, which means there are 10 volts missing in our circuit. The total is supposed to be 30. So if only 20 is found in R1, 10 must be found in R2-3. Well, why is that? Why is it 10 for both? Parallel rules. In a parallel circuit, the voltage is constant. So if there's 10 volts left over, the other two resistors get all 10 volts. Easy. Now, we have a little hole in the table here. We can fill it. Because we have the voltage, we have the resistance. As long as we divide them, the current. 10 divided by 2, 55, and then do the same, so boom. Now, as much as you probably would like to say, oh, we could just split the current in half for that one to the start. That is only happening, right? We're only seeing 5 amps for both resistors because because they both have a resistance of 2 ohms. If R2 and 3 were different values, they would have different currents. Again, if R2 and 3 had different values, they would have different currents. And I'm pretty sure there's a practice problem on that I'll put up later. But that being said, all the hard part's done, because power is just voltage times current. It's kind of boring, right? Nothing really much to do. I guess you can always check yourself. They should always add up. So make sure that all your powers are correct. Add up P1, P2, P3, and match it against your equivalent power. But we've done everything. I know, kind of quick, but hopefully it wasn't too bad. Now that we have gone through one relatively long example, I have a practice problem for you. Go ahead and take a moment, see if you can solve through it. Again, go from the outside of the circuit and work inwards and see if you can figure out what to do. Take some time. I'll be back in a second. And we're back. Hopefully you were able to work a bit, or at the very least identify some of the things that I put on the board now. Again, I've identified resistor 1, 2, and 3, as well as indicated what type of circuit that they're in. I identified each resistor, and now we need to figure out, well, what's going to happen next. First things first, find your equivalent resistance. That's going to be fun. So let's go ahead and solve for the parallel section of our circuit. We have a resistance of 7 ohms and 5 ohms respectively. So 1 over 7 plus 1 over 5. That's going to be R2, 3. Oh, don't forget the negative exponent. That should get you 2.92 ohms. It's really like 2.917, but we'll keep it like this. Next, we have R23 is here. We now need to find the equivalent resistance, or the total resistance. And remember, once we have simplified R23, our circuit looks different. Our circuit now looks like R1, R2, 3. And sorry if that's hard to see, but it just means that, hey, because we reduced our parallel circuit to a simple one, we now have a bigger circuit that is series. Again, we have now reduced resistor 2 and 3 into one circuit. And now, because we've done so, we're just dealing with a series circuit, which is pretty easy to handle. So we're going to take our 2.92 and add it to 3. Get 5.92 ohms of resistance. And that will be our equivalent resistance, 5.92. Nice. Hopefully you were able to get that far. But if you haven't, make sure you get that down and see if you can solve for the current really quick. So now to solve for the current, we need to keep in mind that Ohm's law will always apply. No matter what's really going on, you can always go back to Ohm's law when in doubt, although at some point it's not as convenient. If you don't have this, pause it now so you can get it, because I'm getting rid of it. So to get current, or our equivalent current, we need to take our equivalent voltage and divide it by our equivalent resistance. Well, to do that, we need 30 over 5.92. That should get us 5.07 amps. Oof. Now that we have all our equivalent values, we can start working through everything else. Well, I guess we can go ahead and find the equivalent power. That wouldn't be too bad. So it would just be 30 times 5.07. Should give us 152.1. And if you're not sure how I got that, power equation is just current times voltage. And the power equation is just current times voltage. That's besides the point. All right, so let's see if we can figure out everything else. Remember, this is a series to parallel circuit, and because it is, we can use that equivalent current and copy it into the series section of our circuit. Again, we can do this because the circuit starts out as series, so it should share the current through the entire system. Well, actually, it should have the same current throughout the entire system. Again, because this circuit started with series, the equivalent current should equal the series section's current, or R1's current. All right, that should be much less dramatic. This is what? Yeah, not nearly as high value, but if you remember from the examples above, we know that we cannot find the parallel currents quite yet. We need to go back after we decide, or after we find what the voltages will be. So, first things first, find the voltage of the series resistor, or the voltage across the series resistor. That should be, what, 15.21 volts. How did I do that? V equals 9 times R. Cool. So then let's use our big old brains. We need to figure out the rest of the voltage. And we know, because it's series, all the voltage gets used up for every object. Parallel is different though. So let's start with the series and see if we can find the parallel next. We know that our total voltage is 30 volts. We know that V1 is 15.21 volts. We don't know V2 or V3. But we do know that they are in parallel. And because they're in parallel, if we find the voltage for one, we also know the voltage for the other. If we find the voltage for one, because they're in parallel, we know the voltage for the other. The best way for me to explain this is we can only use whatever's left of the voltage for the parallel. Again, that first resistor is getting in the way. It's eating some of the food before it moves on. It's eating some of those electrons, not really. So we only have a certain number left to spread throughout the rest of the circuit. So if V1 was so hungry, right, it took 15.2, we can only use whatever's left. So 30, 15 to 1. Whee! That shouldn't be too bad. It was like 14.79. Yeah. That's how much voltage we have left. And so because that's all that's left over, B2 and 3 are gonna have to just share it. And so because they have to share, well, they should have the same voltage. Now, this is where things get more interesting. Earlier, I mentioned that, hey, before they had the same amount of current because they have the same resistance. Now we're going to see that if they do not have the same resistance, if all your resistors have different values, your current will have a different value in each spot. So first off, for R2, I got a current of 2.11 amps. For R3, I got a current of 2.96 amps. That is not like the example I showed you earlier, where they had the same number. No. If the resistance is different for each section of your parallel circuit, there should be a different current in each section. Here's now for the easy part, huh? You just have to start multiplying some things to find our power. So starting off with R3, I got a power of 73.95. So a little amendment to what I said earlier. I did not multiply the current and voltage correctly in the original. So this is future me coming back and just putting this up so that you can properly see the power and how it's supposed to be calculated. Again, it's voltage times current. These are the actual answers. So yeah.